right, so today we're going to try to start speaking about support vector machines. I was hoping to cover this subject actually by the end of today, but we didn't initiate any discussion on Thursday, so maybe we have to move on this on Tuesday as well. All right. Before I do any presentation on SVMs, let me say that SVM has been a very successful tool for classification in the 70s and 80s. And if you are ever going to develop any new method on your own, you have no choice but to compare with SVMs. So even if you don't like the method anymore, right, there's no way you can avoid to actually run SVM, which means you need to know what SVM is all about. Okay, so there are reasons why we don't particularly like SVMs, and one of them is that they're not probabilistic in nature. All right, so we know to do things a little bit better than SVMs. All right, so obviously we are exploring this idea of sparsity. So we discussed about the relevance vector machines, and we're going to do the same things with support vector machines. So if you think having a lot of data points, xn, and with different, let's say, kernels considered for the problem, we would like to have a method that is sparse. And sparse means when you do predictions, you only have to evaluate kernel functions of a very small subset of the training data, the same way as relevance vector machines. The nice thing about SVM is that you get a convex optimization problem that has a unique solution. So it's actually a fantastic exercise of learning things about optimization. All right, so we consider binary classification, and we consider the case that is what's called linearly separable training data. So the idea is we can separate the two classes with a hyperplane that is defined by this equation that you see here. That's our generalized model that we have seen up to now. We're going to assume that we have n input vectors x1 to xn. We have target values that take values -1 to 1. So that's one class, one is another class. And the classification is going to proceed if we compute W and P. When Y is greater than 0, so Y greater than 0 will be assigned to the class +1, all right? And Y less than 0 to class -1. But because we want to have linearly separable data, means for all points, the training points that Tn equal to +1, Y of xn has to come greater than 0, and for all points that have labeled -1, Tn -1, Y at xn has to be less than 0. Which means, if you check the two cases, we want basically for all training data points, the product of Tn with Y computed at xn has to be greater than 0. All right? So you can see here, if Tn is 1, all right, Y has to be positive. If Tn is -1, Y has to be negative. So remember, for all training data points, we need to have this thing valid. And obviously, we're talking about the linearly separable case. And when I mean linearly separable, we don't separate the data necessarily. We're going to work in a future space, right? So the hyperplane that's going to separate the data is going to be defined in the future space phi of x. So when we transform this to the space x, it's not going to look a nice plane. It will be something a little bit more complex. Okay, so this doesn't sound as a trivial problem. So if you look at this data here, these blue points, class 1, and the red points, another class, you will see that these dark lines are all possible solutions, right? So all of them are acceptable classifiers because they precisely separate the blue points from the red points. In some way, you can say that even this line that does a little bit of mistake, maybe it's an acceptable solution. So in a probabilistic setting, which we are not, we discussing basically in earlier lectures. All of these things are acceptable solutions, and you may want to assign some probabilities and then maybe compute a solution that is some weighted average, if you like, of all of these possible hyperplanes. Okay? But certainly, we need to deal with the case that there may be more than one solution for this type of problem. All right, so what we need to introduce the concept that is called the maximum margin classifier, right? So we have many solutions, and obviously we need to select a solution that has the best generalization error, and to allow us to introduce SVMs, we have to introduce this concept that is called margin, but it may look weird as we start talking about it. So think the following. These points that you see here are the training data, and we have more of those. So take the hyperplane that separates the blue points from the red points, all right? That's the hyperplane. And assume now that its thickness of that line starts increasing in both directions until it hits the nearest training data points. You follow what I say? We take this, so this is separating hyperplane, right? So think now that the thickness of that line starts increasing, all right, until it hits the nearest training data points. And you can see these training data points are denoted here with circles. So this width that you see here is called the margin. And we're going to use the concept of margin to define SVMs. Okay? So now these points that you see here, all right, are basically the points that you need to have to be able to calculate the separating hyperplane to do classification. All the rest of the points that you don't see them with circles, you don't really need them anymore. All right? So these points are called the support vectors. You remember this is similar to what we did with relevance determination, right? We threw some basis functions out, and we said, you know, a very small subset of the basis functions centered at each point are needed. Here, what I'm telling you is, from all the points, the training points, only the support vectors are needed to define the location of the separating hyperplane. So again, what have we said here is, we define the margin, and I want you to remember if there is another schematic. Okay, there's no schematic, I remove it. So think again, in defining the margin, take the thickness of this line to start growing, right? When you hit the nearest data points, that defines the margin that you see on the left, and the nearest points are called the support vectors. All right, so now I'm going to have to explain the notation here. Obviously, the separating hyperplane is y equal to 0, and then I'm going to explain why this is y equal to -1 and y equal to +1. All right. I don't know if you remember from the early days when we discussed about classification, I introduced this diagram, all right, and separating two classes, class 1 and class 2. So this is the separating hyperplane. One of the things we define geometrically, and you can go back and look at an earlier lecture on linear classification problems. If you take a point x, its distance from the separating hyperplane is given by y of x divided by the magnitude of w, and the magnitude of w is the vector that you see from here to there. Okay, I'm not going to prove it, but basically the proof is, in an earlier lecture, the distance of any arbitrary point x from the separating hyperplane is given y of x divided by w, okay, the magnitude of w. And this is a sign distance because on this side of the hyperplane, y is positive, on the other side, y is negative, right? But I am going to do a modification on this distance, and I'm going, if I take a point xn, I'm going to define the distance as tn times y of xn to make it an absolute distance. Because you remember, what did we say for all training data points, that Tn times y of xn has to be what? Because we're going to separate them exactly. What is the product Tn yn? It's positive. All right, so I'm going to have this distance modified, so it becomes a positive distance by simply multiplying by Tn times y of xn. So basically what this quantity here, right, is nothing else but the distance of point xn from the hyperplane. Okay? And it's an exact calculation, and if you look on the earlier lecture, you will see the derivation of this. So, I wrote this explicitly now, W transpose P of xn plus B, that's what y of xn is, divided by the magnitude of W. So this support vector machines, they are trying to do the following thing. They are trying to, so they work using the margin W, all right? And they are trying to maximize, all right? Look at this problem and tell me actually what it says. You can start with a minimum and then tell me with the argument that says argmax. What does this argument with the minimum does, divided by the magnitude of W? So 1 over this times that, and then says minimum over n. So what are you doing with that minimization? Looking at the equation that I have on the top. So what's going on here? What's the optimization problem inside the parentheses there? You say from all the data points find the one, which is what? From all the data points, right, find the n point, which is what? Which minimizes what? Which is the closest distance to? Remember this, what is this distance we said? Is the distance of an arbitrary training point xn from the separating hyperplane. So you say here minimize over n, so what are you looking here? The what? You're looking to find the training point n, which is what? The closest to the separating hyperplane. All right? So that's what the calculation here does this. And then, so effectively, when you find that, what does it do? It defines what we call the margin. You remember we said take the hyperplane and increase its width until you hit the closest training data point. So what we say now, once you find this margin, maximize it with respect to the parameters W and B. That's basically the whole idea of support vector machines. They're maximum margin classifiers. So you first find the closest point n to the separating hyperplane. Okay? So that effectively defines the margin, and then you say this margin is defined in terms of W and B. Now maximize with respect to W and B, and this will lead us to this whole algorithm that goes under SVM. Okay, now, will you agree with me that if I double the values of W and B simultaneously, that this thing inside the parentheses is not going to change? Right? If you change the magnitude, if you put instead of W 2 times W and 2 times B, will you agree with me that this, the margin basically is not going to change? Look at the calculation, right? If W there, if you put 2 times W divided by 2 times W, you will get the same thing. All right? So effectively, we need to remove this scaling effect out of this calculation so we don't have this issue. And the way to do this is, how about if we arbitrarily define that for the closest point to the separating hyperplane, that Tn times W transpose P of xn plus B is equal to 1. So effectively, it's like, you know, by saying this, it's like we fix what, we get rid of this effect of the scaling in W and B. So we arbitrarily said, okay, that for the nearest point n to the separating hyperplane, Tn times that is equal to 1. Okay? Now, you remember that Tn times y of xn has to be greater than 0 because we're going to separate the data exactly, which means that for all other data points n, this has to be true. Okay? So for the points that define the margin, this is equal to 1. For all other points, this is greater or equal to 1. And here is actually now, so if we set this thing equal to 1, right, we effectively get rid of this, the explicit minimization on the points because we define them like that. And instead of maximizing 1 over w, all right, well, I can pose the problem as follows. Find w and b so that you minimize 1/2 w squared with the constraint that for all data points, Tn times w transpose phi of xn plus b greater or equal to 1. You need to understand this blue statement there, that this is our final statement for this linearly separable case, because the algebra is going to become a little bit more complex as we go along. So let me summarize because we all look like zombies here, all right? So, so this is the separating hyperplane, all right? So now, think that that line starts growing, okay? And it grows until it reaches the nearest points. So when you do like this, this thing defines when you hit the first data point, the first training data point defines what's called the margin. And the points that are in the margin are basically, these support vectors, and denoted here with circles. So we define the distance of a point x from the hyperplane with this equation, and then we said is find the margin first by locating the training point that is nearest to the separating hyperplane, and then once you find that, you find the margin, maximize it. All right, so we rescale it like this, which means this is true for all data points, and then the problem is stated as minimize. Now instead of maximizing 1 over w, you say minimize w squared over 2, looks more appealing that way, with the constraint that for all training data, Tn times w transpose phi plus b greater or equal to 1. Okay. So what I'm going to do is now, I'm not going to give you a review of optimization with constraints. There is a 2-page appendix, I think, on, I don't remember if it was in Bishop's book or in Murphy's book. If you don't have access, just email me and I'll send it to you, that discusses the summary of the equations, basically when you try to minimize or maximize something with inequality and equality constraints. So in our case, the inequality constraint looks like this, right? For all training data points, this needs to be satisfied. So what we do is we introduce a Lagrange multiplier alpha I, and the loss function now is to minimize w squared over 2, and at the same time maximize over the parameters alpha, the Lagrange multipliers, multiply with this constraint. So basically we went from a problem that looks simple with constraints to a problem that basically has involved the constraints inside the loss function using Lagrange multipliers. Now you will have to read a little bit about optimization to know why you maximize with respect to alpha, okay? And it has to do with the sign here and the fact that your problem is a minimization problem. So we minimize with respect to w, and actually I should put there NB, okay? And we maximize with respect to the Lagrange multipliers. Okay? Now if you look at the loss function like that, right? What you can do is you can think of this with alpha, you can think that the parameters alpha are temporarily fixed, okay? Let's say we know the parameters alpha temporarily, so we need to do the minimization with respect to w and b, and the way we do minimization of a cost function is by taking derivatives with respect to w equal to 0 and derivatives with respect to b equal to 0. So if you take derivatives with respect to w equal to 0, you're going to get a w from this term, all right? And from this term, you will get basically alpha I times ti times v of xi. So you get this equation. And if you take derivatives with respect to b, you will get alpha I times ti equal to 0. Okay? So basically, we have done the optimization with respect to w and b while keeping alpha constant, all right? But don't forget, we're going to have to solve a maximization problem for alpha. But now, you know, we basically have these new constraints that define w, and through this equation sort of defines b as well. So you can actually think what we're going to try to do now. We're going to take these two equations, plug them in back to the objective function, and get an objective function only in terms of alpha, only in terms of the Lagrange multiplier. This is our dual optimization problem, right? We went from doing optimization in W and P to now doing optimization only in terms of alpha. So if you actually plug in this inside this objective function, all right, even the b will disappear, because you can see here the b term involves summation of a n t n, which is 0, and then you plug in w, and you use the kernel definition, all right? And what you get is, you get a very nice quadratic function for the parameters alpha, for the Lagrange multipliers, with two constraints. The Lagrange multipliers have to be greater or equal to 0 for all n's, and then the summation of alpha n t n has to be equal to 0. Okay? So this is the dual optimization problem, and it's obviously quadratic programming that you can solve it very cleanly. But you know, if you read the literature, one of the things they will recommend is don't bother to write your own solution for these quadratic optimization problems, because unless you do a lot of tricks and in a very sophisticated manner, you're not going to be able to do these problems in high dimensions with a lot of data sets. Okay? So basically, you have to download an existing code that does this type of problems in a sophisticated manner. Okay. All right. So you can actually show that this optimization problem has a global optima, and but I have not said a word yet. Where is the sparsity coming, and what is this whole idea of defining the margin and maximizing the margin? So, you know, by now everybody's confused. Why is this of any help? Okay, so let's suppose we have solved this problem, all right, in terms of the alphas, and we try now to do predictions for a new x, and we want to compute y of x. Okay, y of x is given like that. So basically, we're going to substitute now w inside this equation. Okay, from where did this come from? Remember when I did the optimization with respect to w, I got this, all right? So w is summation of alpha I ti times v of xi. So if I plug in this on my equation here for w of x, then what I get is y of x is summation of alpha n t n times the kernel defined at the locations x and xn plus b. Okay, where is the sparsity being coming? So before we explain the sparsity from this equation, you remember that we introduced a Lagrange multiplier to enforce this constraint. And when you enforce these constraints, these two things together, you lead to what is called these Ken-Tucker conditions that involve the two constraints plus this identity you see on the bottom. Have you seen this before? When you have an optimization problem with constraints, right? This is what we did here before, all right? We set this thing with the Lagrange multipliers being positive, and we added this constraint, okay? So the Ken-Tucker conditions are these three conditions here, okay? So the Lagrange multipliers are positive. For all data points, this is satisfied. That was my constraint. but also I have an times Tn y of xn minus 1 equal to 0. So the product of the Lagrange multipliers times this constraint is equal to 0. These conditions need to be satisfied at the optimum, and they're called the Ken-Tucker conditions. I know, I think Bishop is calling the Karusk-Ken-Tucker conditions. They're KKT or KT conditions. So again, what I suggest is, if you look at Wikipedia on KKT conditions, you will see immediately on a constraint optimization problem from where these three conditions are coming. So can you look now, this is how I do predictions, and these are the constraints I have. Can you look at this slide and tell me now why this problem introduces sparsity? Just look at these equations very carefully and see why when you try to do predictions, you try to figure out if y of x is positive or negative, right? You want to classify the point x to what class it belongs, so you compute this, and I'm claiming that this equation with these conditions it does not require you to do the summation for all n's, only for some n's. So can you tell me, using these blue equations there, which n's are going to be needed for prediction? All right, so the ones that an is not equal to 0. So if an is not equal to 0, what has to be equal to 0? Tn of yxn equal to 1. And you remember what point n was, what point n satisfy that Tn times y of xn equal to 1? The points on the margin, okay? You remember, if I go back, all right, these are the points basically that satisfy that an is not equal to 0. Which means when you try to do predictions, the only points that you need are the support vectors, that they're on the margin, nothing else. So you can have thousands of other points that actually in many ways are free to move everywhere outside this margin. The only points you will need to do predictions are, let's say in this case, those three circles that you see there. Of course, don't forget that to do the optimization problem, unfortunately, you have to involve all points, but for predictions, you will only need the support vectors. Okay? All right. So this is what more or less it says here. And we haven't said anything about the calculation of B, all right? So we need to calculate B as well. You remember for the support, for these points on the margin, we just said that Tn y of xn equal to 1, okay? So if you plug in y of x equal to this, right? Where lots of these alphas are 0, all right? So what we get is, we get Tn summation of all of these kernel values plus b equal to 1, where this subscript s here is the indices of only the support vectors, the vectors that basically have alphas non-equal to 0. Okay? So you can solve this equation using a particular support vector and compute b, but what is actually recommended is to average this equation over all possible, all support vectors that we have, right? Because you may have more than 1 point on the margin, so effectively what you need to do is you multiply this equation by Tn, and then you average over the support vectors, the same indices s here, and then the calculation for b comes explicit to look like this. Okay? All right. You can write this framework with the quadratic optimization problem and maximizing the margin. You can write this as a loss function, and a lot of computer programs out there, they're actually using sort of this idea directly. So the loss function here, you remember what did we want to do to W? We wanted to minimize W, right? And we had this constraint So if I can go back, all right, and then we have this constraint here, okay? So what you can do is, you can define an error function based on that constraint with an argument t1 of yxn minus 1, all right? And you define this error function such that if this argument is greater than equal to 0, the loss here is equal to 0. So if the point is correctly classified, there is no loss, all right? Otherwise, you make this to be equal to infinity, okay? So you can actually work directly on this minimization of this loss function, and you can get the same identical results that you get with quadratic programming. And actually, in many ways, this may be a good point to start if you want to start doing approximations, and rather than using this loss function as I described it, you may want to put something else there, right? And we will discuss a little bit on this on Tuesday, because it allows us to generalize things to other type of algorithms. So an example, again, so this is the separating hyperplane, all right? And you notice this line here, and this line there, and this line there define what? The margin, okay? So, and what if we want to do predictions of any arbitrary point anywhere, the only thing we need is the data points that we see with circles, right? These are the support vectors. Anything else can do anything they want, right? And assuming they're not in the margin, we don't really care. But unfortunately for training, it's not like it would be fantastic if to train the model, the only data points that you needed are the points on the margin, but unfortunately, we need everything. But for predictions, the only data points that needed is the ones on the margin. So that's how sparsity is introduced on support vector machines. And obviously, you can see here, the separating hyperplane, right, is defining future space, all right? So when you go back to x, obviously this is not a straight line. It's this curved boundary, but you know, there is no difficulties. And I think, I'm guessing here, the kernels defined was probably they were Gaussian kernels, yep, okay? So you have Gaussian kernels to do this problem, but you can use, if you want, something else as well. All right, so again, the same point here, this, you can separate it with, so if this is the future space, right? This is the space phi of x. Let's say if you transpose x, if you transform x to a future space phi of x defined in a 6-dimensional space like that. So in future space, you actually have a linear hyperplane that separates the data, but when you go back to the original x space, you get a curved separating boundary, all right? So it's, in some sense, this is very much needed. You won't be able to exactly separate the data in the x space directly. So you need to go to future space phi of x to be able to do that. And you know, here is using different types of polynomials to, I think, I don't know if it is the same data set, but anyways, if you try to go to the x space, right, and say fit a second order polynomial or an 8th order polynomial, you get all these weird, you know, curves. The only thing I'm going to say right now is that when you try to do this type of techniques and separate, let's say, there are other points here, right? I don't see them. There are some red points, right? Or some white points. So there are two classes here. So when you try to separate them, in essence, separating them exactly because the data are separable, it may not be such a great idea because somehow you may overfit, so your predictive capability may be diminishing by demanding to separate this data precisely. You may want to accept some error, right? I mean, that's the whole idea of machine learning. You accept some error. You don't, you know, care fit everything passing from your training data. So that way, when you do predictions, you can have a better generalization error. All right. So what do we do now if you cannot separate the data exactly? Can these ideas work? Can we extend these ideas? So things are going to get now a little bit more complicated. So first we're going to assume that we're going to allow data points to be on the wrong side of the margin, okay, with a penalty that increases linearly from the distance from the boundary. We're going to introduce what is called a slack variable, one for each data point. So we have the slack variables Cn. For those who have worked on linear programming, or quadratic programming, these are standard variables. You will see in a moment what they do. So we're going to set Cn equal to 0 for all the data points that they are on or inside the correct margin boundary. So you can see here, everywhere here, all the data points are x equal to 0, and on this boundary x equal to 0. Now on this side of the separating hyperplane, x will be less than 1, and on the other side will be x greater than 1. This point, even though it's on the wrong side of the margin, we will accept it as being a blue point. This point that is up there, because it's on the wrong side of the separating hyperplane, we will not accept it. Okay? So for this point, we're going to be committing some error that is defined by this distance x that you see defined here. Okay? So the idea here is we accept some points on the wrong side of the margin as being classified correctly, but other points are misclassified. Okay. So how is this going to help? We're going to, you remember for separating things precisely, right? We wrote this equation before, okay? Now we're going to modify it. This thing inside parentheses is y of xn. So we're going to modify it and write this equation as Tn y of xn is greater or equal to 1 minus xn. Can you see that? So we have replaced this strict condition, right, with this equation, okay, where the only assumption we make is that the distance Cn, all right, is greater or equal to 0. And again, this is my definition here. All right, so Cn is basically an estimation of the error that I do from the label Tn versus the prediction y of xn. Okay, so again, on this side, everything is equal to 0, even on the margin is equal to 0. On this side of the red line, x less than 1. On the other side, x greater than 1. And these points are classified correctly, and this point is misclassified. And it will give me an error that's proportional to the magnitude of this line that you see. Right, that defines xi. Okay, so the optimization problem that we discussed before has to be modified, and now we want to minimize the constraint that you see there. So tell me where this term comes on this constraint. First, the term w squared over 2, what is that? From where is w squared over 2 coming from? It's identical as before, so what is w squared over 2? I mean, here we minimize, but if was to maximize, we'll be maximizing 1 over w, and where is 1 over w coming? You remember these are maximum margin classifiers, so what, what is the w squared term coming from? So, but what is, so the margin involves the term 1 over w. So really, by minimizing w squared over 2, we maximize the margin exactly as before. But now, in addition to that, we say minimize the summation of xn's. So what is this summation of xn's do? remember, Xns are the distance of the points that they are on the wrong side of the margin that may be accepted and classified correctly, or misclassified, like this point that you see up there. So sigma of Xn is basically the the amount of error I'm doing in having points on the wrong side of the margin. It's like trying to minimize the misclassification error, right? And we write this misclassification error in terms of this slack variables. Okay? And so that's the optimization problem, basically. The only change from what we did before is the way this term looks like. Okay, before we had another penalty term that was enforcing this constraint directly. Now the constraint is written in terms of Xn. By the way, you can do exactly what you see here, even for separable data, all right? You will get exactly the same analysis, but this is extendable to the cases where you allow misclassification. So the summation of the Xns is an upper bound on the number of misclassified points, okay? Because for all misclassified points, Xn is greater than 1. So when you sum this thing, it will be higher than the number of misclassified points. Okay, very fast. We want to optimize this, we want to minimize this, and we have these constraints using the slack variables that they are greater or equal to 0. So we're going to introduce Lagrange multipliers to this optimization problem. So what does that Lagrange multipliers means? We have one inequality, so we're going to introduce Lagrange multipliers alpha, and we're going to maximize with respect to alpha times this constraint. And then I have another constraint that Xi is greater or equal to 0. So I'm going to introduce another Lagrange multiplier mu that's greater or equal to 0 to enforce this constraint. So now we have a problem that has multiple unknowns. We have the W, the B, the Xi, the Lagrange multipliers alpha, and the Lagrange multipliers mu. All right? So what you do is you write down the Kern-Tucker conditions, all right? And the Kern-Tucker conditions basically, what I want you to concentrate is the third equality here and the sixth. And can you immediately see that this model will introduce sparsity? So can you tell me, I mean, it requires a little bit more algebra, but what points will have alpha n non-equal to 0? Because using this equation, either alpha n is going to be equal to 0, or this is going to be equal to 0. Right? So, so tell me for what points n you think this parenthesis is going to be equal to 0. Say it again. On the boundary, misclassified.
And then slightly like inside the boundary, like inside the margin.
Inside the margin and correctly classified. All right. So it comes out, if I can find it somewhere. All right. So the points basically that are remaining are the points inside the margin that can be either correctly classified with Xn less than equal to 1 or misclassified with Xn greater than 1. So points like the one that you see here with Xi less than 1 and points that are misclassified with Xi greater than 1. And the analysis is actually sort of straightforward, just looking at that equation and looking at some of the remaining Kern-Tucker conditions. All right. If you take this complex optimization problem, if you want to write it in the dual form, and you want to get rid of W, B, and Xi, you can take the derivative with respect to W set equal to 0, the derivative with respect to B set equal to 0, the derivative with respect to Xi set equal to 0. Take these three constraints, plug them in up there, and then what you get, actually, you get a quadratic loss function, all right? And the quadratic cost function has two constraints for the coefficients alpha n. alpha n greater than equal to 0 and less than equal to C. But the way C, if I can go back here, C, the inverse of C plays the role of regularization parameter. Can you see that? Because usually when we do optimization, right, and we regularize with this norm of W squared, that's where we put the regularization. So you can think 1 over C being a regularization parameter. Okay? So, alpha n is between 0 and C, and then alpha n times Tn equal to 0. And again, the predictions, as we discussed, involve a very small subset of these points alpha n. Okay. The calculation for B, it's slightly more involved. So, so if you start, let's see, on the support vectors that have Cn equal to 0, so that this is true, all right? So this involves the support vectors, and then if you multiply this by Tn, and then if you sum over the points that lie within the margin, okay? And again, when you follow the algebra, you will see these are the points where alpha n is strictly greater than 0, less than C. You get an expression that looks similar to what we had before, okay? The two indices here are different because this is the support vectors, and this set is only the points for which Cn equal to 0. Okay, there is an alternative sort of formulation of this that comes from a completely different setting without using these maximal margin calculations. And the alternative formulation basically gives you the same results. I'm just going to state this SVM formulation. You have the second term that we had before on the loss function in terms of the alphas, but the actual conditions here are a little bit different, okay? And this coefficient nu is a new coefficient that somehow serves as an upper bound on the fraction of the margin errors and also as a lower bound on the fraction of support vectors. So this formulation basically is used actually more often than the standard formulation that we saw before, but practically they give similar results. Okay, and again you see another classification result using Gaussian kernels. So in this problem, I think I show you this problem for comparison when we discussed about the performance of RVM versus SVM. You notice here that the support vectors are too many, all right? So RVM does way better than SVMs. Here the circle points are too many, and in any event, this is the two margins that that are defined like that, and within you have points that are correctly classified as well as points that are misclassified. Okay, we don't need the optimization details. All right, can you do, I mentioned actually that one of the limitations of SVM is that there is nothing probabilistic about it. So there is a literature on trying to make support vector machines probabilistic, but they are literally very artificial. So you can think if you try to produce sort of a posterior probability of T being in class 1 given for any test point X, what you can do is you can take the output of a support vector machine that I call here Y of X and pass it through a sigmoid, right? That's logistic regression. So and then you can say, okay, fit this on one, fit the support vector machine on one set of data, and then compute A and B on another set of data. So it comes out that if you do this, the results don't look very exciting. Okay? So you can look at the original publications. If I can go directly on a very simple problem, there's a little bit of details here that you may want to read, but what you have is if these are the class conditional probabilities, okay, and you see this is I'm plotting this log, all right, versus, so this logs versus, this is x, I will assume, right? It's since these are uniform distributions from 0 to 1.5. So this ratio is supposed to be looking like this slide line, all right? This is the exact answer, and you notice RVM manages to get the solution very close to the exact solution. SVM gives you basically garbage in this problem. Even though it gives you garbage in the prediction of the separating plane, somehow when it comes to doing predictions, the misclassification error is the same for RVM and SVM, but in this plot it tells you that you cannot really rely heavily on this type of probabilistic interpretation of SVM. All right, there are a little bit of very few details that I need to tell you on Tuesday, including how to use SVM for regression, and then we will move to ideas from lasso algorithms and generalization of sparse models. So things will get a little bit more interesting as we move along. All right, so that's all for the day. So I'll see you on Tuesday.